Hi, I'm Toshit, a research associate working with Professor Vijay Natarajan at the Visualization and Graphics Lab, IISc. I'm here to present a recent work titled pyParaOcean, a system for visual analysis of ocean data. In the field of oceanography, visual analysis has become an integral tool for exploring model simulations, detecting phenomena, and tracking dynamic processes. However, as data sizes continue to grow and multivariate dynamic data becomes more accessible, there's an increasing demand for scalable and flexible visualization tools. We present pyParaOcean, an extensible and scalable system for visualization and exploration of ocean data that aims to provide the right tools for comprehensive understanding of oceanic processes and phenomena. Ocean analysis is crucial for understanding climate, marine ecosystems, resources, and environmental health, enabling informed decision making and sustainable practices. However, visualizing ocean data has some challenges. We need more efficient algorithms as the size of dataset grows. There are complex features to visualize, like fronts and eddies, and there are multiple interdependent scalar and vector fields. There exist plenty of systems for ocean data analysis. Cove is one of such systems that supports interactive exploration over web and has 2D and some 3D visualizations. However, its capabilities are limited by WebGL. Red Sea Atlas is another 2D interactive visualization tool of a Red Sea. It has different views for properties like winds, waves, tides, chlorophyll, etc. Ocean Paths is a data visualization tool that computes pathways, tracing ocean currents, and supports the plotting of different high-dimensional data along those pathways in 2 dimensions. Vapor is one of the few tools that provides efficient 3D visualization for oceanography, but has limited extensibility and scalability. While we recognize the availability of several methods for ocean data analysis, we note that they are often standalone solutions. We aim to leverage the extensive advancement in visualization technology as implemented in Paraview by providing functionalities and views that are specific to ocean data. We introduce the design of ocean data analysis system that is pyParaOcean. It has various modules for ocean data specific visualizations such as eddy identification, front tracking, vertical section views with parallel coordinates plot, and field lines visualization with various seeding strategies. The system is designed to be extensible, that is, the new modules for ocean data analysis can be included and integrated into the system in a seamless manner. The system leverages the computational benefits and functionality of Paraview to cater to the ever-growing sizes and resolutions of ocean data. Finally, we demonstrate pyParaOcean in action as a case study on the Bay of Bengal. Paraview is a robust and a fairly established tool in the visualization community. However, it is a steep learning curve for someone who does not have a background in visualization. It does provide parallel computational capabilities that we aim to leverage. Let's take a look at the design and architecture of pyParaOcean. It's a 3-tier architecture with a client, a render server, and the data server. The data server is responsible for all the data-related tasks such as reading, writing, and filtering. The render server is responsible for all the rendering tasks, while the client manages the creation, execution, and destruction of objects on the server. The benefit of such an architecture is that when you have large datasets, you can run the server on a different headless machine, such as a cluster or a supercomputer. If you have more specific needs, then the data server and the render server can also be run on different machines. Let's take a quick look at the UI elements of pyParaOcean. The views are on the right. This is where you see all the visualizations that you create. You can open multiple views at once and they can be linked together as well. In this particular case, the views we see here are put together automatically by pyParaOcean. The line chart view shows the depth profile curve between multiple variables and depth. The parallel coordinates plot displays multidimensional data along depth, allowing for exploration and comparison of multiple variables simultaneously. We see all our 3D renders in the render view. The pipeline browser shows our data and all the filters that we've applied on our data. The properties panel displays the filter specific options. For example, here it shows the coordinates where we want to drop a needle. The interface feels very familiar to someone who's used Paraview before. Now we take a look at the modules for ocean data analysis in pyParaOcean. Streamlines are a set of integral curves tangent to the velocity at every point in space. They portray instantaneous lines of flow that characterize important oceanographic phenomena such as eddies, currents, and filaments. To initiate the computation of streamlines or path lines, seeds are sampled from the domain that act as starting points for field lines. Sampling can be uniform and weighted. For example, you can highlight highly turbulent regions by seeding more points in regions with high vorticity. Another parameter for highlighting turbulent flows is the Okubo-Weiss parameter, which provides a more comprehensive assessment of flow patterns and turbulence in fluid dynamics compared to vorticity alone. As a result, it highlights more eddies. If we seek points weighted by flow magnitude, then we can see streamlines where the speed is high. Or, if we seek points in the regions of high salinity, we get the streamlines that look like this. We can see the salt water coming in from the Indian Ocean into the Bay of Bengal. A path line describes the path a massless virtual particle would take beginning from the seed position at a particular time step. Path lines are useful for understanding transport such as salinity advection and debris collection. After seeding the seeds through the seed placement tool, temporal ID is assigned to the particles and this filter tracks them over time steps. We see the path lines in the Red Sea in this figure. The seed points are uniformly seeded. They are colored on the basis of temperature, and we can see how the path lines build on top of the path lines from the previous time step. There are two very dominant eddies in the Gulf of Aden at the bottom right. We can see the path lines for the particles in the Gulf of Aden terminate into those two eddies. Now we take a look at the eddy identification tool in pyParaOcean. A mesoscale eddy is a circular, spiral-like oceanic current pattern, typically spanning tens to hundreds of kilometers in diameter. The eddies have a high velocity along the boundary and the velocity goes to minimum at the center. In this figure here, we see a depth slice in a region in the ocean with the color indicating velocity magnitude. The minima are shown by the dark colored points. The eddy identification tool is designed as an extensible tool which allows for multiple implementations. In the current implementation, it uses the speed scalar field to find the minima for eddy centers. Then, the unwanted minima and noise is removed by topological persistence simplification. This is done for all the depth slices and for all the time steps. Finally, seed points are seeded near the detected eddy centers and field lines are rendered on the basis of an approximation of the winding angle criteria by checking if a streamline crosses into all four quadrants of the xy plane centered at the minimum. The field lines are terminated on the basis of its distance from the eddy center. This module aims to both compute and effectively visualize the eddy. In this figure, the streamlines are colored on the basis of velocity magnitude, and we see multiple small eddies here surrounded by a larger, more significant eddy. Fronts are volumes of water with distinct temperature or salinity characteristics. A surface front is the boundary of a scalar field isovolume. Understanding their movement is crucial for ocean data dynamics and processes. Visualizing the movement of surface fronts helps in understanding ocean circulation patterns. Surface fronts serve as an effective representation of high salinity water masses. This filter tracks the fronts over time and generates a tag graph that summarizes movement of all surface fronts. This figure here shows different high salinity surface fronts in the upper Indian Ocean. The larger component is significant as it moves into the Bay of Bengal, as we'll see in the case study. We now present a case study on the Bay of Bengal using the filters and modules from pyParaOcean. Here's a rough schematic of the major currents and eddies in the bay during the monsoon season. The lighter yellow color is the landmass, the Indian peninsula, and Sri Lanka is the island on the bottom right. A large anticyclonic eddy is located to the right of the southern monsoon current, and a cyclonic eddy, known as the Sri Lanka Dome, is to its left. In this case study, we focus mainly on the anticyclonic eddy. The anticyclonic eddy is 500 kilometers in diameter and is characterized by intense downwelling owing to its anticyclonic circulation. The anticyclonic eddy starts forming in June, develops into its circular shape in July, and weakens in August. Let's take a look at how the anticyclonic eddy recirculates salt into the Bay of Bengal. We visualize the same using the high salinity isovolume colored in white, and the streamlines are colored on the basis of speed. We can see the anticyclonic eddy forming and transporting huge amounts of salt water into the bay throughout the month of July. We now take a look at the effect that the anticyclonic eddy has on the 27-degree isotherm. The depth profile filter is useful when the user wants to study some properties along the depth. To see the effect that the anticyclonic eddy has on the 27-degree isotherm, we use the depth profile filter from pyParaOcean and drop a needle at 7 degrees north and 84 degrees east. The points of interest can be brushed from the parallel coordinates plot, and all the views are linked together. The anticyclonic eddy pushes the warmer water down, and we can see a depression in the isotherm traveling towards the left. This is also evident as the line chart view starts to flatten. Now, we explored the anticyclonic eddy in the Bay of Bengal using the eddy identification tool. Dissipation of the anticyclonic eddy in the Bay of Bengal through August 2020 can be seen in this animation. Streamlines are seried near the detected vortex cores to show the evolution of eddy profiles in 3 dimensions. We now track the movement of high salinity cores in the Bay of Bengal. One of the components of the surface front moves towards the east coast of India near Visakhapatnam. The evolution of the surface front component is computed and visualized as a track in this animation. In summary, we presented pyParaOcean designed as a Paraview plugin, offering oceanography-specific visualization and analysis functionalities, efficient computation, and access to general-purpose filters for visual analysis. We demonstrated a case study on the Bay of Bengal, showcasing pyParaOcean's capabilities in exploring eddies, ocean currents, and salinity movement. In the future work, we plan to expand the filter options to include additional statistics computations that are important to an oceanographer and conduct correlation studies to investigate relationships between different oceanic variables. We want to develop capabilities for temporal data analysis to explore time-dependent patterns and trends, and conduct scalability tests with higher resolution ocean models to ensure plugins' effectiveness in larger datasets. We aim to prepare for the release of pyParaOcean as an open source software to facilitate wider adoption and collaboration. Thank you.